This, I think you guys did this lab in chemistry class. Yes? Okay. If you recall, shut up. I mean, can I have your attention, please? If you recall the specific heat of something, the reason why it's called specific is that it's specific to that substance, so you can tell what type of substance it is by its melting point, boiling point, its density, and its specific heat. And to do that, you just take the thing, usually you heat it up in a hot water bath so you know that it's 100 degrees Celsius, and then you drop it in here, and that thing gets colder and this thing gets warmer, and you measure the temperature rise, and yeah. And then this is an insulated thing that keeps the heat from leaving this, so you are heating up air and all this stuff, right? Let's do a more simple problem. But here's the basic concept, right, is that the heat lost by the hot stuff is equal to the heat gained by the cold stuff. They're going to go back to the same, they're going to reach the same temperature and equilibrium temperature. And they do that just because the heat just sort of mixes up. And when it gets all mixed up, it's going to be, and we'll talk about this later, it'll be the same temperature. So let's do, and rather than write all of those words down, why don't we draw a picture of it. Here's how I like to draw the picture. So you've got this cup. Apparently it says neglect the calorimeter cup. So when you did it in chemistry, I bet you used a styrofoam cup, right? If you do use an aluminum cup, then you've got to like incorporate it, and the calculation's a little harder, right? But this is a styrofoam cup, and it's got 0.481 kilograms of water. Kilograms of water at 18 degrees Celsius. Right? And then we've got this stuff. It's an unknown substance. You know it's unknown because it's got like a question mark on it, right? Okay. And this stuff is at 98 degrees Celsius. And it's 0.231. Right? And this is going to go in the cup there. And these guys are eventually going to go to a temperature of 32. Like that. So this is going to go up to 32, that'll go down to 32, right? And then I like to set them up this way. I'll say that heat lost equals heat gained. So it's lost by the hot stuff. So 0.231 kilograms times C that we don't know. And then what's this change in temperature from 98 to 32 is 66, right? 66, right? And then we've got to do the water, so we go 0.481 kilograms times 4186 joules per kilogram degrees Celsius, right? And then this change from 18 to 32 is 1214, exactly. Okay. There we go. Now notice that the C, everything on the right side evaluates to what units? The right side is all joules, isn't it? Eventually it becomes joules, only joules, because it's MCAT. And then you're going to go joules divided by degrees Celsius divided by kilograms. So this thing will have the units of joules per kilogram degrees Celsius, right? So take your calculator and calculate that by touching your calculator in a not weird way. Oh, the year was 1848. How I wish I were in. So we have 2 sig figs, do we? That pains me to write this, because it's so close to rounding up or down or something like that. Is that what you guys got? Didn't it pain you to round that down because of 2 sig figs? I'm like, I get it wrong. I like round it to 1850 or something like that. Actually, you can on the IB test. You can do that. You can be off by 1 sig fig. Certainly, if you're going to use this number later, use this guy. That's not so bad. Is that bad? one way, another way they set it up too, sometimes people will set up, notice how this is really a negative change in temperature and this guy's really a positive change, right? So sometimes the teachers will teach you to do it, this plus this equals 0. In other words, the net heat loss is 0, right? I like to do it this way, but because it's the way I always did it. But that way is the same. So then you would make this a negative and that a positive, and of course it'll add to 0. So. All right, let's have you guys try. Oh, I don't know. We already did one where we solved for C, so let's solve for... oh, that one's going to be harder. Now, notice in this one that it's not just the water, it's also an aluminum calorimeter. Yeah? Yeah? So let me give you a clue here. Sometimes, class, sometimes they'll give you a problem where you can't ignore the mass of the calorimeter cup, especially since they give it to you and they give you the specific heat of it, right? Can't ignore that, right? So what we would do in this case, I'm just going to make it up, right? Almost always it's the right side, the heat gained, has more than one thing. You rarely like throw 2 different unknown metals into the thing, right? Okay, so this side here, okay, we've got, we would add, we go 0.257 times, what's aluminum, 900, right, times, and then its temperature change. These guys on this side, they'll all have the same temperature change. They'll have different masses and different specific heats, right? So you can set up. This is not the setup for that, obviously, because I just tacked on a term to the example we do. See if you can solve for the mass of the mipsolipsium. This is the specific heat of mipsolipsium. It's so funny because people rarely remember that element. There actually is a mipsolipsium mine in Oregon. Yeah, you're going to go MCAT plus MCAT. So you're going to go MCAT equals MCAT plus MCAT. We used to have for a long time, Paula Collins had drew a picture of MCAT. It was like a cat with a cape on that said M, like Superman, but it was MCAT. It was up there for a long, long time.
Oh, it's
Gadinius, the red-headed stallion. Okay, so we don't know the mass of the mipsolipsium, right? But we do know. Let's see. Okay. The hot stuff. No snoring. The worst thing is like if you find that you're snoring in some public place. He wants me to light a firecracker. Oh. What is this? 4.1? Is this 4.1? There we go. So isn't it going to be all this whole side just divided by this, divided by this?